In topic 2, we're going to take a look at graphs of functions. And again, we might recall that throughout this, where in the past we had y equals mx plus b, we're now going to substitute the y with the function symbol, and we get a graph of function now. So if we have something like example 1, g of x equals, and we can convert the 0.5 to 1/2. If we were going to graph this, we would graph the y-intercept, which is a -3, and we would go over 2, 1, 2, up 1, over 2, up 1, over 2, up 1, and we would get, we only need 2 points to make a line, but we would get the graph of this function. And notice we had the y-intercept there, and the x-intercept happened to fall into place. And here they're stating that this would be the formal way to write the function. And since it's a straight line, x is to the first power, our y here would have been to the first power. It's a linear function. All right, now we're going to take a look at this piecewise linear function, where we're going to often deal with two formula in function form and then plot them. So in example 2, we have, in a sense, two statements of function. F of x is this, f of x is this, and then there are what we call qualifiers, that for this part of the statement we say x is less than or equal to 2. So as we mentioned way back earlier, we could make a t-chart to illustrate this. So I have that here. So what values would we put for x if x is less than or equal to 2? Well, we know it's going to be a 2, then a -1, a 1, I guess, a 1, and then a 0. And we could make more, but these are plenty. And we'll do that shortly here. Now let's look at the second part of the piece, which is this function and this qualifier, that x is greater than 2. Now here, 2 is not included in the set. So what I'm going to suggest is that we put the 2 there, but then put like a little circle to indicate that it's just to the other side of 2, but we're going to get a value for 2. And then we're going to say, since it's greater than 2, let's say 3 and 4. That would be enough to get a line. So we start to fill it in. If x is 2, 2 plus 1 is 3, 1 plus 1 is 2, and if x is 0, this would be a 1. Now here we have x as a 2, so -2 times 2 is -4. -4 plus 7 is 3. And we're keeping in mind that's our value, but it doesn't quite start there. It's just to the other side of this. Now, negative 2 times 3 is negative 6 plus 7 is a 1. And negative 2 times 4 is negative 8 plus 7 is a negative 1. So there are our values. And again, they're showing it to you a little different way. I like this way. This is what we're used to. So now let's do this one in blue on the graph they provide. So it's going to be 2, 3. So 1, 2, 1, 2, 3. Now for this one, we're going to just put a circle there. And the reason is that this point is not in the set. There's a circle there. And then 3, 1. 1, 2, 3, 1 is right there. And then 4, 1. 1, 2, 3, 4, right there. So with my line tool in blue, I'm going to make this part of my piecewise. And it's much better the way they do it. Now let's use red for the other piece. Now here, 2 is in the set, 2, 3. So we go 1, 2, 1, 2, 3, but now we're going to put a dot there in red. And this is 1, 2, 1, 2 right there. And then 0, 1. 0, 1 right there. So in red now, we're going to make our line. And it's this line here. So we have the two pieces. Now, one of the things we're going to look at is this a function? Well, they say it's a function, but are the x value used more than once? So as we go along this line, the x values are just used once. And you might say, well, wait a minute, aren't they used twice here? Well, remember, 1 is a hollow. We're anchoring it there, and it's coming out from there. So it's not used there, but for the other value it is. And for the domain of this will be from negative infinity to positive infinity. And for the range, just a little review, it's coming up here from negative infinity, and it goes all the way up and stops at, we project this over to our y-axis, and we get 3, and that is a bracket. And for example 3, we're going to set this. So here we've set this up with our function statements and our qualifiers. So now we're going to put values in there. Here, if x is less than or equal to 3, this will be a 3, 2, 1. And here x is greater than 3. We'll anchor it to the 3, but again, put this little dotted area indicating that is not part of the set. And then 4 and 5. So, looking at this, putting it into our function, if x is 3, 3 minus 2 is 1. If x is 2, 2 minus 2 is 0. And if x is 1, this will be a negative 1. And then here, if x is a negative 3, this will give us a 5. If x is a negative 4, this will give us a 4. And if x is a negative 5, this will give us a 3. So now we plot it. 3, 1. So 1, 2, 3, a dot right there. 2, 0, a dot right there. And then 1, negative 1, a dot right there. And it gives us this line. So this is a piece of this piecewise function. Now 3, 5. 1, 2, 3, 1, 2, 3, 4, 5, and see, here they're using a little circle. That's not included in the set, but a place to anchor it. And then 4, 4, and then 5, 3, and that gives us our next line. Now again, is this a function? Well, they're saying it's a function, and it passes that the x values are only used once. Here it's used solidly as a 3. Here it's just anchored. It's not a 3. Okay, piecewise function. Now again, we're doing absolute value, where our function is y equals the absolute value of x. And we worked on these in previous sections, and we said we write it without the absolute sign, and then we write it just saying this side is the opposite, that is negative. So again, our qualifiers, x is greater or equal to 0, and here x is less than 0. So this value right here is not really included in the set, but anchors it. So if x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2. And then here, if x is 0, y is 0. But again, that's just a starting point. The 0 is not included in the set. And then here, if x is a negative 1, the opposite of a negative 1 makes it a positive 1. And the opposite of a negative 2 makes this a positive 2. So when we put this on a graph, this part of our piecewise, this piece, gives us this, a solid dot there, this one, and this one, and of course creates this line. While the other, this, it anchors it to 0, but that would be the hollow for this part, and then over 1, negative 1, up 1, negative 2, up 2. So this gives you the general shape of your absolute value function, which we said is the V shape. And it is a function because at 0, the 0 is only used once. Here it's just the anchor, would be a hollow. And a little review, what's the domain of this? The domain would be from negative infinity to positive infinity, because this line eventually goes way out there. And for our range, it's starting at 0, and will go up eventually to positive infinity. Just a little review. At this time, we're going to introduce a new vocabulary word called step functions. And in this case, the greatest integer function, and it's written as that instead of absolute signs, we're using brackets. So this designation indicates a bracket around the x is defined by saying the greatest integer function denotes the largest integer. Remember, integers are whole numbers and they're negative values that is less than or equal to x. So less than or equal to x. And here are the examples. The greatest integer function of 8 is 8. 8 is an integer. The greatest integer function of 7.45. Now that's a fraction, it's a real number, but it's not an integer. The greatest one equal or less than that would be 7. The greatest integer function of pi, which we know is rounded off 3.14, would just be the 3. Of -1 would be -1. Now here's where it gets a little tricky when it's negative. Negative 2.6 on a number line, there's a -3, there's a -2. So the negative 2.6 is there. So equal to or less than or equal to is going to be the -3. And that's how it is developed. So, graph the greatest integer function of x and consider the values between each two consecutive integers. So in this first case here, the greatest integer function, x is in the middle here. Now, what would it be? Well, anything that occurs in here, for it to be the closest integer that's less than or equal to, would be your -2 here. And then as you go through these others, it is summarized in this table. And I'm not going to create this graph for you, but let's just study it a little bit. So for this item, between 5, less than 5, and then greater or equal to 4, this is the step table, step function that we see, and it would be for this value. Now notice, this is not an absolute sign. These are brackets. This is to indicate step function. And once again, is this a graph of a function? And notice that the x values are only used once. So yes. In example 6, they're showing us postal charges to send a flat envelope first class to any of these places for a fee of $2.05 for up to and including the first ounce. So here $2.05, and we'll see that down here, up to the first ounce. And then when you start after the first ounce up to the second ounce, they're showing you how they have placed that. So this is a function. Again, the x values are only used once, and this is how it's shown. So this is another example of step functions. Now, for graphing other functions, we saw straight line, we saw V-shaped graphs. Now there's going to be other shapes, parabolas and curves, and for graphing these functions, here is a protocol to follow. First, determine the domain of the function. Select some points, include both negative and positive ones, and then you plot the points, and then that'll give you the general shape of the graph, and then you make an educated guess about the entire shape, and unless you have been informed to the contrary, assume that the graph is continuous, that is, unbroken, unless they give you a qualifier of some type. Okay, so we'll take a look as we move on here to the graph of a parabola, and in this case we're going to start in example 7 of a graph of a radical example. Now keep in mind, when you have one that looks like this, there are some qualifiers. Remember, under the radical sign you can't have anything that makes this less than 0. So we had discussed this earlier. We're going to say x minus 1 is greater or equal to 0. So when we solve this, we get x is greater than or equal to 1. So our domain for this will be bracket 1 comma positive infinity. So we're going to start with a 1, so that's what we put in our t-chart. A 2, and we get a few values so that we can start to plot that, and this is our graph. And we have seen this before, but now a little more definitively here. Now as we look at example 8, would there be any values that we would have to dismiss here, or is our domain all real numbers? And it's all real numbers. So to get the shape of the graph, we're going to need a number of points where we put these values for x into this formula, and we come out with these values, enough to give us a shape. Notice when x is 0, whatever our y value is our y-intercept right there at 3. Okay. Now we can also do piecewise things, and we've done this already. This is just a little more complicated. Setting up your t-charts using these qualifiers, and when we do that, the graph looks like this. Let's get to see it just a little bit more. Now here, since x has to be greater than 2, we don't start at this positive 1 here, where normally it would. and we're careful about our x values have to be less than or equal to 2. And it gives us this funny shape here. Notice it's still a function. The x values at 2 are only used once because here there is a hollow. So some of these would take quite a bit of time. Again, you want to understand the process of what's going on and then the resulting graph. So this information in your notes and of course in your textbook is a good reference. In example 10, they're taking a look now at reading a graph and looking this over. So the questions that they're asking here, how do the prices in the West compare with those in the Midwest over the period shown? So there's the West, and then there's the Midwest. Well, generally the prices in the West were higher, and they're indicating that by $100,000. And in both regions, prices declined until 2009. That is a slight dip. And then in 2011, the gap between the two regions had shrunk to just over 50,000. Well, we know in 2008 there was a big burst to the housing price bubble. So here it's just 50,000. All right, which region typically had the highest prices? Well, here they're asking in general, and we see it is the Northeast, where we live. Okay. So in example 11, once again, we're going to take a look at this graph, and this indicates the mortgage rates, and we see a steady decline of what is shown here. It starts in 1985, and these are 2 years apart, so we have to estimate here between the lines. Find the function values of 1988. Well, 1988 would be right there. We go up and it's right on the line at 10. And then 2009, right there. Going up there, going over 5%. So quite a difference. And then during what period were mortgage rates at or above 7%? So here we look at 7% right here. And then all the way to 2001, from 1985. And during what period were mortgage rates at or below 5%? Well, 5% is right there. And it looks like from 2009 to 2011, and of course 2017, they're still low. Now, for our last topic, they're giving us something easy. And this is called the vertical line test. It's a way to find quickly whether or not something is a function or not. And the way it works is you take a very thin imaginary line, which I'm calling this red line here, and move it over the face of the graph. Well, this is a sideward parabola. Now, as this line comes over this graph, does it intersect this graph in more than one place? Well, yes, it's intersecting it here and here, and here the one they're showing you is there and there. Now, notice at this place, the 3's are used twice. So we say that this shape of graph has not passed the vertical line test. So this is not a function. And let's go on to look at the others now. Does this pass the vertical line test? Yes. So this is a function. Does this pass the vertical line test? No, that's not a function. Now, how about this funny shaped little line? It almost looks like these are in the same place, but eventually this goes off and this goes off. So this does pass the vertical line test. And they give you the explanation here. Now, one thing I'd like to do to wind this up is one of the graphs or the series of graphs that we've done we had a positive slope, a negative slope, a zero slope, and an undefined slope. Now, which of these would pass the vertical line test? With this one? Yes, this is a function. Positive slope. How about this negative slope? Yes. How about horizontal or zero slope? A horizontal line? Yes. These are all functions. How about the vertical line? Now, when that vertical line went over it, it would coincide an infinite number of times. So this does not pass the vertical line test, and a vertical line is not a function. Okay, you'll have your quiz-me's and things as we continue to work on Chapter 3.